Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. Click on the person icon to learn more about today's speakers. Throughout the presentation, you can network with others or submit questions to the speakers in the Q&A and chat box next to the slides. Download resources from the cloud icon. After the webinar is over, please take our survey to tell us how we did. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Need Help? Email us. If you experience any technical issues today, please refresh your browser by hitting F5 for PC or Command R for Mac. And now I'm excited to turn it over to today's moderator.
Good afternoon, and welcome to this webinar, UPS and Power Considerations for Harsh Environments. This event is brought to you by Mission Critical and sponsored by Eaton. I'm your moderator, Amy Al-Khatib, editor of Mission Critical. Thank you for joining us. Today's presenters are Ed Spears and Jay Queen from Eaton. Ed is Product Marketing Manager for Eaton's Critical Power Solutions division. He has 35 years of experience in UPS systems testing and power quality engineering for telecommunications, data centers, cable television, and broadband public networks. Jay is the single-phase product manager for modular IT and industrial OT UPSs at Eaton. With his degree in electrical engineering, he has designed and collaborated on many products from gasoline pumps to computers. Don't forget to submit your questions, and later in the program, our presenters will address as many as possible. Today's event is being recorded and archived on www.missioncriticalmagazine.com/webinars. And now I'm excited to turn it over to today's first presenter, Ed Spears.
Hello, everyone, and welcome. We would like to thank Mission Critical for giving us the opportunity to talk with you today about uninterruptible power supplies and power distribution for harsh environments. As many of you that are on the call may know, that a lot of the applications historically for UPS systems have been computers and data processing. But as those applications move into a mixed or hybrid environment or a distinctly harsh environment or factory floor automation, other manufacturing environments, which are a lot different than inside the clean space of the data center, the UPS systems that we consider for those capabilities need to be modified as well, and we want to talk about some of that, those considerations with you today. So we'll be talking a little bit about the technologies that are involved, what's the same and what's different, what's changing. We'll be specifically thinking about UPS products for oil and gas environments, as well as UPS products specifically for marine and water-based saltwater applications, et cetera. And towards the end, we'll take a little bit of the time to spend on dual-purpose UPSs, where the UPS system is used for more than just a battery backup and power conditioning system. So questions come to mind. First of all, what is the environment that we see here? Well, it looks more like a factory environment or industrial environment, and the requirements for mission-critical devices that need to be supported are just the same, if not more so, than what we would find in a typical IT environment. In fact, today we find ourselves knee-deep in the IIoT. Now, you may be familiar with the Internet of Things. The IIoT is the industrial Internet of Things. Many, many, many devices be communicating amongst each other and to the infrastructure in the facility and outside. And not only that, but the security and the ruggedness and hardiness of these communications is even more important than it would be in other applications like commercial home applications and that type of thing. So the industrial UPS perspective is it's time to think outside of the data center box and make sure the products are going to work in these more difficult environments. Examples, of course, manufacturing, test equipment, drives, machinery, some of that heavy machinery, things like different power factors and different inrush requirements and things like that are a little unusual to what many of our operators are used to seeing with the UPS system. Another application, of course, is transportation and mass transit. That's signaling. You see the bullet train there, automation and controls, instrumentation and IT, and of course, unmanned vehicles or self-driving vehicles. And as you can imagine, some of these requirements are actually life and death. So it is absolutely critical that the power system remain available and rugged even under harsh environment conditions. Petrochemical is another case where we see a lot of requirement for UPS systems, for instrumentation, and also for the process equipment and testing that is heavily used in petrochemical applications. And then, of course, marine systems. There's things like emergency lighting, helideck lighting, video communications on large cruise ships, and of course the navigation systems, which, as you can imagine, are absolutely critical. So the requirements we see are changing in a manufacturing environment, different levels of loading capability, different voltage regulation requirements. Those types of things are different than they were even 5 to 10 years ago in process and automation plants, in warehouses, food processing, where the cleanliness and the accuracy of measurements and those types of things become very important. And then there's, of course, mission critical power for things like wastewater and water quality plants, 911 centers, large scale banking, and of course, rugged environments for military and defense applications. So smart industry and automation has arrived. No longer is this the old-fashioned technology that we would deploy old-fashioned UPSs to work with. Quite a bit of sophisticated communications are involved here and secure communications. And what that often means is the UPS system that I might have procured 20 years ago might still work from a functional standpoint, but would have problems meeting the communication requirements and the user interface requirements in this new environment that we find ourselves. So on this slide, we list a few features that are common to industrial UPS. And as a vendor of this type of equipment, along with our competitors in this market, we're constantly trying to determine exactly which of these features are needed for all types of mechanical or industrial UPSs and which ones might be optional. We want to make sure that we provide a product that meets the client's needs. Of course, Jay and I both work for product management, and that means it's our job to assure that the products meet the needs of the clients, and products that are in development and under the development process need to choose features and capabilities that align with what the client requires. When we do our Q&A toward the end of this session, don't be shy. Let us know what you feel would be the best type of features and capabilities for industrial products going forward. But mechanically, we see things commonly like a thicker zinc-coated or corrosion-proof plating on the exterior and the interior surfaces of the machine. The paint and finish would typically be powder-coated or something even tougher than that. Typical paint processes for sheet metal would usually not be effective enough at eliminating the possibility of rust and corrosion. The air filtering against in these machines needs to be protected against dirt, dust, and water. And IP 23, 33, and 54 are commonly requested capabilities for the enclosure for the machine. And sometimes that means that the UPS system gets placed in an exterior box with the appropriate filtering, doors and gasket seals, and the appropriate finish on the outside. Seismic tested cabinet solutions, NEBs, or Zone 4 or OshPod, any and all of those are commonly requested and specified for industrial UPS. Pre-engineered vibration dampers for marine use. So what this means is, instead of the UPS sitting on casters or on leveling feet, they're actually rubberized or flexible vibration dampers, and the UPS would be bolted to the floor of the building or the deck of the ship and would be supported not only at the bottom, but often at the top of the cabinet as well, in such a way that it can absorb vibrations and shock and vibrations much more severe than you would find in a stationary environment. Cabling and accessories from the side instead of just from the bottom or the top, commonly requested. Front access, which is almost ubiquitous in the UPS industry today, only requiring front access for all installation and all service activities is a given in most UPS applications, industrial or otherwise. Now, what about electrical requirements? different kilowatt ratings within a product range. So the UPS is rated and matched exactly the power requirement that the client intends for. Voltage, even without transformers, typical voltages we see in this part of the world, 120, 208, 380, 480, and of course 600 volts up in Canada and in some cases here in the US. And with optional internal transformers for both input and output, then the ability to go as high as 690 volts for the input to that UPS is typically required. The three-phase input and output can be single-phase or three-phase on the output, so it is common to request a three-phase input and a single-phase output, typically a four-wire, three hot wires and a neutral and ground, or what's called an IT distribution network. And then battery voltages anywhere from less than 120 volts DC to beyond 480 volts DC, both in cabinets or racks. The 120 volt DC requirement is very common because it matches the typical voltage that you might see in a station battery in a factory or a manufacturing environment, and the client is going to want to use that large battery that he's made a big investment in to power the UPS. And the question is, can the UPS run from that DC voltage, or does it need a different voltage like 240, 120? Small UPS might be 12 or 24 volts, but 120 and 125 volts DC are very common. Typical larger UPSs use a 480 volt DC input. These are the kind of things that might change in a industrial rated UPS. Some other key features: in harsh environments, needs to be operated in an ambient temperature that is well beyond the 0 to 40 degrees C or 32 to 104 degrees Fahrenheit that we see with UPSs. And remember, the battery is more sensitive to temperature than the UPS power electronics is. In many cases, the battery temperature range, which can be somewhere close to 75 degrees Fahrenheit, will dictate where the UPS is deployed. But in these particular applications, many times you don't have that option. You simply have to place this in a warm environment or a cool environment. So what do I do about those batteries? Are they going to have a shortened service life? Are they going to have less backup time in a very cold environment, for example? So that needs to be considered up front when you're deciding how to deploy the UPS and where to deploy the UPS. Now, as you probably know, lithium batteries, for example, do operate successfully over a typically wider temperature range than do traditional lead acid or valve regulated lead acid UPS batteries. However, it is still wise to keep that temperature within a range of about 65 to 85 degrees Fahrenheit, because the longer service life and warranty that comes with a typical lithium battery installation is based on a reasonable temperature range. So yes, if I have to operate at a much higher temperature range, maybe 35 C or 40 degrees C, then a lithium battery will give you better performance than a traditional UPS battery. However, if you want that full service life from the lithium battery that you're typically paying extra for, then you need to make arrangements to keep that temperature in a reasonable range. So, conformal coated PCBs and a protected touch-sensitive HMI display. By touch-sensitive and protected, we mean the kind of thing that it's protected from salt spray and water and corrosive environments on the display itself, so the display functions and is clearly visible and easy to use, even with a protective cover over it. Conformal coated PCBs, the circuit boards in the UPS would be sprayed or dipped in a coating that makes them much more resistant to not only dust with metal particulate in it, but also corrosives. And while we're talking about corrosives, we do want to at least make the point that even if you have conformally coated PCBs in the UPS, there's many other electrical connections inside that are still going to be sensitive to corrosive environments. And so you want to pay close attention to the vendor's limits and the application requirements and how much, if any, corrosive gases are present in the air where the UPS will be located. To that end, one of the ways that you can make the installation safer and more reliable is to use Hepa air filters, or very low particulate air filters. So if you are in a high dust environment or a corrosive environment even, you can filter out some to all of those objectionable particles. That also means that those filters cannot be ignored over the service life of the UPS. There needs to be a functional repeatable maintenance process for checking those filters every 30 days or every 3 months, whatever the environment demands. Redundant and monitored cooling fans. So the failure of a fan doesn't eliminate the ability to filter the air or cool the UPS. We need redundant fans, and we need to monitor those fans, not just when they stop turning, but when they start to slow down or begin to age. It would be nice to notify the client in advance that I've got a fan that's slowing down and needs attention. Let's do that now before the fan actually stops turning. The other things that you see in electrical environment is a higher capacity rectifier, one that can charge the batteries faster or do so in a higher temperature environment. Same thing for the inverter, a higher capacity inverter that takes the DC from the battery or the rectifier and converts it to AC for the UPS output. Needs to be rated to handle perhaps higher inrushes, motor loads, the presence of variable frequency drives, etc., on the output, and a load that changes rapidly. This is a little more of a challenge than it would be, for example, in a UPS that sits in a data center or a network closet, and the load is relatively constant day in and day out. These industrial loads tend to be widely variable and have some very, very high inrushes. That needs to be taken into account, again, at the system design stage. Enhanced overload capacity, the same idea, at least optionally. I need to be able to handle a higher overload peak for a longer duration, make sure that matches the application. One of the things that means is that you're looking at pumps and motor loads and moving assembly lines in a factory, compressors for air conditioning and cooling and heating. Those kind of things are more likely to be placed on the output of the UPS. So we need to know up front what's the worst case condition in terms of inrush, make sure the UPS is sized to be able to handle that, and to be able to handle that even when it's running on batteries and has no utility present, transition to if it gets overloaded. So these are complicated questions sometimes that need to be addressed early on in the process. Other things like an internal or a sidecar mounted or a wall mounted wraparound bypass. Just as important in any UPS application is a wraparound bypass, also known as a maintenance bypass. It should ideally be separate and isolated from the energized circuitry inside the UPS so that I can de-energize the entire UPS for service without interrupting power to my critical devices and without having any live componentry inside the UPS so I can service it safely. Input circuit breakers or switch contactor may be standard or optional. It's become relatively common in the IT business to eliminate the input breaker and just use fuses and contactors, and recognizing that there's an input breaker on the wall beside the UPS typically. But in industrial applications, you're more likely to see a request for the input breaker and output breaker, for that matter, be internal to the UPS, even if it's redundant to external breakers the client may have. Another common feature is a battery start. In other words, the ability to start the inverter on battery without any utility power present, sometimes known as a cold start capability. There's certain industrial applications where it's handy to be able to run the critical load, at least for a short period of time, off the UPS battery, even when incoming utility power is not present. And it's more common to see lifting lugs. You see them in yellow in the picture on the right here. Those lifting lugs allow the cabinet to be picked up from the top. Many UPS cabinets today are riveted or bolted construction as opposed to welded frame, and not all of them are amenable to being lifted from the top plate. But it's very common in industrial applications and shipboard applications to require those lifting lugs. Here's an example of a typical specification, and the part that's highlighted here is the input harmonic distortion. In other words, the harmonic distortion that the UPS system rectifier throws back on the source that feeds it. In highly industrial applications, distortion is common. We don't want the UPS to contribute unnecessarily to the distortion in the building, because that can impact other loads that don't happen to be on the output of the UPS. So the requirements commonly in the US is that input distortion, or THD for total harmonic distortion, must not exceed 5%. So we talked a little bit about heavy-duty rectifier. Nowadays, UPSs use active rectifiers instead of diodes or SCR type connections. And the input THD is controlled to be less than 5%. and the input power factor near unity are about 0.99. So this decreases losses in utility cabling and transformers. No need for reactive power compensation or harmonic filtering on the front end of the UPS, which improves reliability and reduces cost and slightly improves efficiency. It eliminates generally the need for greatly oversizing the generator. Doesn't mean the generator doesn't need to be a little bit bigger than the UPS, at least 1.25 to 1.5 times the size of the input capacity of the UPS. But dramatic generator oversizing should not be required if the UPS utilizes an active rectifier. And it also gives and allows a wide operation range. It'll accept input frequency from, say, 40 hertz to 70 hertz, and a voltage from maybe as low as minus 25% of nominal to as much as 20% of nominal on the high end, plus minus 25 to plus 20%. So lots of advantages to active rectifiers, and not all designs, especially for industrial, are using those types of rectifiers, but the more modern devices is much more common. So it's a good feature to look for when you're comparing UPSs. The high capacity inverter we already mentioned, mostly to be able to handle high inrush and overload conditions. Low output voltage THD, we were talking current THD on the rectifier. The output voltage, we're thinking more in terms of voltage distortion rather than current distortion. More kilowatts or a higher output power factor compared to a traditional industrial UPS, which might still be rated for 0.7 or 0.8 power factor. The ability to handle unbalanced loads, sometimes severely unbalanced loads. Modern transformerless UPSs should be designed to take as much as 100% on any phase, regardless of the percentage on the other phases, and handle a high unbalanced current. Remember, though, that if you exceed 100% on any of the three legs of a three-legged UPS, you are going to get an overload alarm, and the UPS is going to take action to transfer to bypass, even if the other two phases are not as heavily loaded as the one that's over 100%. The UPS system should also act to correct low power factors for the critical load, so that the UPS would typically have the ability to correct for low power factors, even if it's in high efficiency mode, for example. And the way it does that is the UPS can be set up to act like a set of noise canceling headphones, where we sense the harmonic presence and the power factor of the load and take action electronically to correct that, like an active power factor corrector, which is a commonly seen device in industrial applications, whether it is a UPS system or not. So let's take a look at some modern industrial UPSs using our own product lines as example here, but there's many competitors in this industry that make very rugged, very capable UPSs. But in the small range, single phase, typically 3 to 20 kVA, one of the things that we see commonly, and we like to see, is a ferro-resonant technology. Ferro-resonant technology is not new, but it's common in this application because it is so rugged. It has the unique ability to do things like ride through brief outages and blinks without requiring special controls or without requiring a battery, at least for the very shortest types of interruptions. It also automatically regulates its output voltage even as the input voltage changes, and does so without the needs for complex controls that might be failure prone or subject to age degradation, etc. Ferro-resonant transformer has the ability to absorb surges and lightning strike style transients without the necessity for having traditional surge protection devices built in. So a ferro-resonant transformer using primarily a special transformer and a capacitive tank circuit provides voltage regulation, ride through with brief outages, surge protection, all without the need for complex controls that could suffer in harsh environments. That's why ferro-resonant UPSs are so attractive for this application. The thing that needs to change in this industry is a lot of these designs are very old. Ferro-resonant transformers are not new. They were invented back in the 1930s. But modern UPSs need to communicate, as we've mentioned before, in this world of the Industrial Internet of Things, or the IIoT. So a nice and functional and useful and remotely monitorable communication section in the UPS is more important than it was in previous times. So the kind of things to look for in an industrial UPS, the ability to hardwire it, of course, or plug connect. if that's what the client wants to do. As the UPSs get larger, they'll move to all hardwire input, output, and battery connections. But a plug-connected UPS can be found in the lower range under 10 kVA specifically. Digital voltage regulation, the capability to handle power factor corrected loads beyond what the Faro does on its own, and line conditioning mode so the UPS can be used to clean the power without a battery. So if the client says, I don't want to invest in a battery, I'm not sure I need it yet, but I do need power conditioning, can I get a UPS that I have the option to add battery later, or that will still function if the battery's disconnected temporarily for whatever reason? That's a key feature for this type of system as well. Standard enclosures, at least NEMA 1, in some cases much more resistant, chemical resistant enclosure, but you're looking for things like not just casters and leveling feet, but locking casters. These UPSs are heavy like all UPSs, and you do not want them rolling away. So locking casters are a requirement. You see casters that don't lock, that's a bad sign. If I'm in a shipboard or high vibration environment, I may have no casters at all, in which case you would expect to see vibration dampers or isolators, which again are rubberized, usually disc-shaped devices in place of the wheels and leveling feet on the bottom of the UPS. And if it's a tall cabinet, there'll also be braces near the top of the cabinet. Option for a NEMA 12 or an IP52 enclosure, 50-degree C rated electronics, and much more expensive, but a battery that can operate with a reasonable service life at 50 degrees C as well, are the kind of things that we see very often. Temperature extremes are probably the biggest difference between an industrial UPS and a traditional data center or a medical grade UPS. So speaking of batteries, what features should we consider? What kind of battery voltage does the customer already have if they have a station battery? They may have invested heavily in a large 48-volt DC battery in a telecom application, and they simply want to hook the UPS's DC input to that station battery. Same thing at 120 volts DC for a lot of manufacturing and factory floor automation applications. The challenge there is that most modern UPSs benefit from having a higher DC voltage because it reduces the switching currents and increases the reliability and efficiency of the UPS. So in many cases, the customer may have a station battery available, but they end up deploying a dedicated battery at 480 volts or 240 volts DC, especially for the UPS. And the question is, can that battery handle the temperature extremes in that environment? So the UPS system should be designed to support both its own internal batteries in the size range and external batteries from a multitude of vendors and a multitude of types. Maybe NiCad batteries are supported, lithium-ion batteries, other chemistries. It's the kind of thing you can check out with the UPS vendor, and they can respond with information on what types of chemistries are acceptable. It's also common to see blocking diodes in an industrial UPS. That's the case where the UPS is connected to a large station battery, and the user does not intend for a small UPS to be charging that big battery. So the blocking diodes are placed in the DC circuit of the UPS to allow the battery to discharge into the UPS to be converted to AC during a power outage, but it does not allow the UPS to push power back onto that battery. In other words, it doesn't allow the UPS to charge the battery. That's handled by other charging stations that are part of the building electronics that support that battery. So diodes are like a one-way valve there that allow the battery to discharge into the UPS, but it blocks that UPS from charging a big external battery. Okay, moving on here. Just like in any application that we've seen in the critical power market, footprint is more important than we expect. So taller, slimmer systems are usually more desirable, but you have to keep in mind in some of these environments, the ceiling is going to be lower. The vibration, and particularly in marine environments, is not going to allow a tall, slim UPS unless it is bracketed at the top, as well as vibration isolators on the floor. But in general, if you have a choice for a smaller footprint, the client is going to be more likely to use that because footprint is king. It is more common, though, to see, especially in the 3 to 20 kVA, a little bit wider, not too deep UPS system that's stable on its own without requiring any external means of support. We talked a little bit about wraparound or maintenance bypasses. These can be anything from a circuit breaker panel on a wall to a pistol grip switch inside the UPS, or the one we see here uses switches that can be locked into one position or another to make sure that no one tampers with the maintenance bypass switch when it's in maintenance bypass mode, and also provides a more foolproof method making the transition from the UPS internal bypass to the wraparound bypass. The circuit breaker type maintenance bypasses have the slight disadvantage of allowing, possibly unless Kirk key interlocks are used, allowing the case of operator error, where somebody operates a breaker in the wrong sequence and disconnects the critical load, which is not why we buy UPS systems. So rotary switches like the kind you see here are common in industrial environments, and they basically force the proper sequence of operation as you turn the switch from the UPS position, for example, to the bypass position. Just a little more foolproof operation. We talked about modern HMI displays that are rugged enough to handle harsh environments. I need to be able to splash liquid on them and basically drop them on the floor a few times. This is a removable display that has a cord connection, so the user doesn't have to bend over double to access the information that he or she needs. So a display that can be remotely monitored and even controlled is more common in industrial applications than it is in computer and IT applications. An LED status bar is becoming more common on all UPSs today, where the user can, at a glance across the room, see immediately by color coding if the UPS is functioning properly. Typically, if it's green or blue, in this case, that means everything is good. If it's yellow, it means there's an alarm condition. And if it's red, it means it trips off. Most of our clients today don't have time to stop and play with their UPS every day. So they need to be able to see at a glance if everything is okay or not, and then go on to their next task. So feedback buttons that provide some haptic feedback that don't allow you to watch for something to change on the screen when you press a button. This is not your home dishwasher. It is an industrial device and needs to provide tactile feedback or haptic feedback for all of the buttons and controls, and support remote deployments, remote monitoring, and remote control, as we mentioned. So the ability to extend the range of the controls with something straightforward like a Cat5 connector, which is commonly available and can be transmitted over long distances, would be desirable. Back panel features are access for connections, terminal blocks. If I'm going to hardwire it, obviously I may have a cord and plug and wouldn't need the terminal blocks. The ability to have an extra battery cabinet or battery system connected, and to be connected in such a way that doesn't provide a safety hazard or doesn't cause a safety hazard. These are the kind of things that UL covers when the UPS system is listed for UL 1778 or other applications. If you're going to have a termination, a plug-in termination for extra batteries, it cannot be the kind where you can inadvertently poke your finger into, for example. So it needs to be a quick disconnect usually, but also needs to be safe, whether the battery, external battery is connected or disconnected, regardless of the status and operation of the UPS. A DC disconnect itself or a circuit breaker for that external battery should be available on the UPS externally, so the operator can disconnect the battery at any time. Communication card slots. So this is something that in the older days was not really considered beyond just an RS-232 port. For an industrial UPS today, communication is very important, and the security of that communication is paramount. So I'm not just looking for a communication card necessarily, but one that has passed the stringent UL or IEC requirements for communication security. Additional serial port, however, is often still included because in many applications, that's still the kind of communications that they use. But by itself, that's usually not enough for a new installation. The ability to do remote emergency power off, front panel emergency power off, contacts to tell whether the generator is feeding the UPS or the utility is feeding the UPS, terminal blocks to accept that information, typically by dry contact as opposed to an analog signal level. And then for flexibility in the application, for the output of the UPS, it's great to have a output panel that can be removed and replaced by the user, and where the user has the choice for what receptacles and circuit breaker sizes they need. So on a UPS this size, traditionally a little bit too big to come with receptacles on the output. But if you can arrange for that and have it something where the user can select those in advance or change them if their needs change down the road, that becomes a very helpful feature and improves the flexibility and, frankly, the longevity of the UPS in that application. So here's an example of what those might look like, where on the back plate of the UPS, you may have one or more positions where I can mount some pre-designed or pre-specified sets of output receptacles and circuit breakers to support those, and they can be mixed and matched both at the factory and hopefully in the field as well as the client's needs change. One other thing that we see frequently for very small industrial UPSs is the need to wall mount them. If the UPS is, say, less than 2 or 3 kVA, typically I'm not going to want to set that on the floor in a harsh environment. I'm going to want to put it on the wall where I have better access to it, where I can keep it out of the way of water and corrosive liquids and things like that. But I need to be able to have it protected adequately, and I need to be able to secure it from prying fingers and button pushing folks who are not sure what they're doing there. So what you see there is an example of a wall mount kit that can be designed and put in place around the UPS and its battery and extra batteries and distribution if needed, that can all fit in the same enclosure and be mounted to a sturdy wall that can handle the weight and provides the ability to put the whole thing up off of the floor. Because remember, as we said, footprint is king. So let's take a look at a little bit larger industrial UPSs here, what we'll call the mid-range, say from 20 to 150 kW. These are typically 3-phase input, and most of them are 3-phase output. We do see in the 20, let's say the 10 to 30 kilowatt range, surprising number of industrial clients where they're feeding a single-phase panel on the output of the UPS, and they're requesting a 3-phase input and a single-phase only output. Now, that's absolutely fine from a functional standpoint. The UPS can be designed to do that. What you want to be aware of is if that UPS has a bypass circuit, it goes to the utility bypass when the utility fails, then that single-phase load is going to fall on only 1 or 2 legs of the bypass source. And the upstream bypass source handle that type of unbalanced load. We want to consider that before we deploy this type of UPS. When the UPS is online and operating normally with a single-phase output, it's going to act to distribute the incoming power evenly over the incoming 3 phases. So that's fine. But when that UPS goes to bypass, that single-phase output load is going to appear across a single leg or a pair of legs of the bypass source and may create a problem that you don't realize is there until you transfer to bypass. So if you are considering a 3-phase in, single-phase out, it is possible to procure those from a variety of industrial UPS vendors. Far more common, though, to see 3-phase in and 3-phase out, especially in this 10 to 200 kVA range. Marine UPSs up to as large as 200 kilowatts. Some of those are 3-phase in and single-phase out, at least up to 30 kilowatts. More likely to require a special IP54 enclosure. It's important to have ultra-high efficiency in any UPS. They may have a 400-volt DC link to match up with some of the DC systems that are operating on commercial ships for that type of transportation nowadays. Another thing we want to be careful about when specifying marine UPS is how the grounding is to be done. In some shipboard applications, the ship's hull is not intended to be used for grounding for power infrastructure. So how would the UPS's input and output be grounded for safety and for safe servicing and for isolation of things like communication cards and that type of thing needs to be considered at the time of the specification for the UPS. So DC UPSs, which are basically rectifiers, 24 and 48 volts for telecom and cell phone towers, 110 and 220 volts for higher station type applications, and then DC distribution options for the output of the DC UPS, and options for the input 3-phase or single phase and automatic transfer switch interaction and that type of thing need to be considered for DC UPSs. So if we overview some typical products that are intended for marine use, you can see on this slide that there are some there are some registrations and certifications that will make it easier to have that UPS accepted for a marine installation. A lot of these are European and Far Eastern certification bodies, in large part because a lot of the shipbuilding industry is taking place both in Europe and the Far East, especially for the cruise industry, which is actually a common application for industrial UPSs. So we would want to choose a UPS that offers those certifications and has been tested in the harsh environments that we see on shipboard that we might not see in an inland factory, for example. So three-phase, single-phase UPSs, rack mount, standalone, vibration isolator mounts. If you look closely, you can see the vibration isolator mounting at the bottom and in some cases at the rear of these UPS cabinets. The general technical specifications for mid-range size UPSs: efficiency in the mid-90s, input current distortion less than 5%, seismic rated either zone 4 or OSHPOD for here in the US, cabinet construction IP32 or 42, maybe 54 for marine applications, humidity 0 to 95%, and it should also say non-condensing. That's a lot tougher in a industrial environment. The presence of water inside a UPS is always going to be a problem. You can conformally coat the boards and put grip shields over the top of the machine or the front of the machine. But in general, humidity that condenses inside a UPS, no matter how it's designed, is going to be a potential for what could be a catastrophic failure. So we want to try to keep that humidity in a non-condensing range. Otherwise, the UPS should be positioned as a box within a box to where the interior of the box can be controlled for humidity. Ambient temperature up to 50 degrees C, some requirements even higher. One of the things we didn't mention earlier on, but if I'm using a rack-mounted UPS or some of my critical equipment is mounted in an equipment rack, then the in-rack distribution strips that might be installed in the back of that rack are going to be in the airflow on the hot side of that critical equipment and can be very, very warm. If you've ever crawled around the back of those equipment racks, it's extremely hot back there, and the installation and the type of power distribution equipment needs to be rated for the temperature that they'll be subjected to day in and day out over their entire service life. Overload capability at least 125% for a few minutes, maybe higher. Keep in mind that if we see an overload that's greater than 125 to 150% for more than a few seconds, that means there's a problem on the output. Not the kind of thing where you want the UPS to sit there and grind away into an overload for 3 days. You want that problem to be solved by clearing a downstream fault or transferring to bypass so that we don't run the risk of overheating or causing the UPS to fail. But it's typical to see overload capabilities from 125 to 150% for some period of time to handle transient overload. We've talked about conformal coding for the PCB. Maybe not every PCB is conformal coded, depends on the client's requirements. Some things like surge suppression devices and that type of thing may not have a conformal coding, but the control and the power circuit PCBs would typically be conformal coded. And then for clients that need isolation transformers on the input or the output or both, much more common to see that requirement here in industrial UPSs. Is it because the UPS needs the transformer to be rugged and work properly? Not necessarily. But if the client does require, for example, common mode noise isolation, a transformer-free UPS is generally not going to provide a very high level of common mode noise isolation. So a transformer needs to be placed in between the UPS and the critical load we're supporting. So whether that's put inside the case of the UPS or deployed separately, that's going to be the best way to improve common mode noise isolation, and that depends on what the critical load requires. It is common in this industrial world to see a specification that says thou shalt have galvanic isolation in the source that feeds this critical device. That means a transformer is going to be necessary, whether it's in the UPS or supplied separately. So UPS systems with transformers, they can be placed on the rectifier input, final output, the bypass input, any combination of the above. And some cases that'll require lineup and match cabinets. Other cases, the transformer can be supplied in a typical gray industrial enclosure, make sure it matches the site conditions. for NEMA rating or IP rating. Some transformers can be set up for positioning up against a wall. Other things that you may see beyond transformers is an industrial battery cabinet that's both stronger in terms of the frame of the cabinet and the sheet metal of the sides and doors. Either analog or digital meter accessories. Surprisingly, we do see occasionally a specification that says analog meters are preferred. Most cases nowadays, we see digital metering because of the accuracy and the ease of reading. But we do have clients that are traditionally conditioned to analog metering and feel that they'll survive a little bit better in a harsh environment. So this is a case where we are occasionally called upon to provide analog metering. Maintenance bypass switches, either external or wall-mounted beside the UPS, always recommended. And connectivity and relay cards for communication that can be certified to be high cybersecurity and hacker-resistant type communications. Some clients in cold environments, of course, require an internal heater be mounted inside the UPS or inside the battery cabinet. And then that cold start feature where I can start the machine from the battery cabinet is another place where that gets used. Modular UPSs are very popular in the IT industry because of their flexibility and scalability, pay-as-you-grow architecture. They're popular in this application as well. Clients today typically don't want to over-provision on day one. They have any ability to be able to plan for the future without investing a great deal of money on day one. That way they know they have the peace of mind of knowing that they can expand the capacity or the battery runtime of this UPS if and only when they need that capability without having to rip it out and start over again with something bigger or something different. So a modular UPS, which if you're not familiar, a big white or black box with a bunch of little UPSs inside that allow them to be slid in and stacked up vertically or horizontally or however, so that I can add more kW capacity and more battery capacity if and when needed. And maybe space for a transformer in the bottom part of the cabinet if the application requires it. We talked about lifting eyes before. Here's a good picture showing what we're talking about here, where we have eye bolts in the top of the UPS. And that usually means the frame of the UPS is a welded frame as opposed to a bolted frame, especially if that UPS contains heavy things like batteries. But the client says, look, I don't have provision for fork trucks to come and move this around on a pallet underneath the UPS. I need to lift it with my crane. So those types of requirements are common as well, much more so than they would be for IT equipment. Okay, so ease of management, we've talked about this a little bit already. First of all, the display on the front of the UPS should be rugged, should be resistant to water and corrosives and things like that. It should have a reliable action to it, either haptic sensitive buttons or touch sensitive color LCD screens that allow you to do more and see more and provide more metering and more alarm and status information than you would find with the traditional front panel, which might have LED lamps and a one-line diagram printed on it in paint. That kind of technology has kind of gone by the wayside in all UPS applications. But an awful lot of our clients are not physically present to interact with their UPS, so they need to be able to get good, reliable, accurate information from anywhere, including their laptop at home if it happens to be on the weekend or something like that. So communication cards that snap into the UPS and have multiple ports so I can install multiple communication cards. Maybe I have 2 different networks on site and I want to be able to communicate over each of those independently in case one network goes down. So the ability to have multiple communication cards in a given UPS is important. It might be BACnet, it might be Modbus, it might be SNMP, it might be just dry relay contacts that can be programmed. That kind of communication capability, you want to be able to say yes to however the client wants to communicate with their machine. So the end user may have a particular device or a particular type of building management system. The UPS needs to be flexible enough to talk to that and provide useful information. And one of the other things you see in the lower right-hand corner is a temperature and humidity sensor. This type is very common for a lot of brands of UPSs, and it connects to the UPS with a simple RJ45 connector. And of course, it'll sense temperature and humidity levels in a battery cabinet, for example, is a good place to use that. And in addition to its sensing capabilities, this one shown has a couple of dry contact terminals so that if I have a device like maybe a water sensor or a door open alarm or something that I want to communicate back to the UPS and then onto my monitoring network, I can do that by simply connecting the dry contact wires to my temperature and humidity sensor, and that information will be transmitted back to the UPS along with the temperature and humidity information. So lots of flexibility with these type of devices, and there's a wide variety of them available. So let's look now finally at the large capacity industrial UPSs. They're going to be physically bigger, heavier, and going to be more likely to contain transformers and going to need more space available for connecting input-output bypass and battery cabling and terminations, especially if they're running at 208 volts rather than a higher voltage. So this range we see up to 200 kVA, and in some cases beyond that. The ability to parallel, just like in any large UPS system, can be important for both redundancy and the ability to expand capacity. A lot of cases, clients are growing faster than they expect, and they don't want to over-provision on day one, so they need the peace of mind of knowing I can add extra of these UPSs if and when I need them without having to rip out my existing and start over all again with something larger. Efficiencies in these type of products get up above 97%. If they have an energy saver mode, then they can exceed 99% efficiency, which means very, very little heat loss from the UPS. So it's going to be easier on the air conditioning system, or the UPS is going to be less likely to overheat its own environment. Remember, we still want to keep these UPSs below 50 degrees C, assuming they're rated even that high. Customization to meet application requirements. I need one transformer, I need two transformers, I need a high capacity rectifier, but I don't need a high capacity inverter. The ability to customize on the fly is very valuable because no client wants to over feature a UPS with capabilities and features that they won't need or don't plan on needing in the future. So this particular one shown here uses 50 kilowatt building blocks and can have 4 50 kilowatts UPSs in this one enclosure, which is about the size of a refrigerator, about 36 inches wide. And then also a wide range of accessories, output distribution, input filtering that is custom, special air filtering on the front and the top possibly, the ability to deploy this box in a larger exterior box with climate controls and special filtering, for example, and maybe even extra batteries in that same enclosure. It's all about the ability to customize. It would be wonderful for this part of the industry if we could standardize on a single set of features for industrial UPSs. But our experience and our competitors' experience has been that clients have a wide range of features that they care about and a similar size range of features that they simply don't need and aren't willing to pay for if they don't need them. So that means the ability to have a flexible design with lots of external line and match accessories becomes pretty valuable on installation day and convenience for the end user and the entity that's selling the UPS. So here's a set of typical dimensions in handy millimeters here. Like I said on the previous slide, about size of a refrigerator. Common accessories, same as for the mid-size UPS, seismic rated battery cabinets, built-in temperature sensing or use that temperature sensor and humidity sensor we mentioned before. Transformer cabinets for the input, output, and or bypass that line and match with the UPS, and availability of higher IP rated cabinet construction. So the value of these features, let's review real quickly. Do I need transformers? If I can avoid transformers, the maintenance bypass might have enough room to be mounted inside the cabinet, but in most of our applications, we like to see the maintenance bypass or the wraparound bypass external from the electronics cabinet because it's safer to service. If I'm able to avoid the use of transformers, my system efficiency can be improved significantly, as can the size and weight, as you can imagine, by removing the transformers. And that would impact the price as well. But if I've got a specification that requires galvanic isolation, or if I need common mode noise isolation, for example, then a transformer is going to be required. And then I can always put a transformer next to the UPS in a commercial enclosure. But most of our clients would prefer to have the transformer, if it's associated with the UPS, be in a line and match cabinet or internal to the existing UPS cabinet. So we'll see some examples of that on the next slide, I believe. The flexibility we talked about, high overload capabilities, longer overload withstandability, and that basically means a derating of the UPS hardware to handle longer term overloads. and to handle those overloads at 40 degrees centigrade or beyond. Temperature is the biggest enemy of overload capacity. We could guarantee our UPSs were all operated near freezing temperature. We could double the kilowatt rating from a given machine. But we have to be able to operate under overload for many minutes at a time if necessary without overheating, shutting down on over temperature. So it's important that the temperature environment and the overload capacities are considered and make sure they don't interfere with each other. Marine UPSs, as you can imagine, should be able to cope with dripping water, spraying water horizontally, high humidity conditions, airborne dust that might be corrosive, significant vibration in shipboard applications, significant tilt in small boat applications, might tilt more than 10 degrees, for example. Anything more than that would be a pretty violent environment for the people on board beyond just the UPS. But those are things to be considered. Most UPSs are not designed to tip more than 10 or 15 degrees without risking some dislocation of componentry inside. Ease of installation still important, just like it is in data center UPSs. Halogen-free cables supported for international applications primarily. Double cabling for double neutraling, things like that, if that's required by the application. We talk about lifting lugs, air exhaust, either from the top or the back, user selectable at the time of order, typically, not usually convertible in the field. Front access for both installation and service. All operations should be able to be done from the front. Internal transformers and anything that helps lower my cost of installation. Having the transformer built into the UPS, for example, is going to be a significant reduction in the amount of pipe and wire that has to be used on site. So a product that scales in kilowatt capacity, both vertically by stacking smaller UPSs in a bigger box and horizontally by putting these larger boxes side by side and connecting their outputs in parallel, again, for increased capacity or redundancy. Tailored solution. Client says, I need to buy a lot of these, but I need them to have certain features. In this case, this client wanted pink paint. All of the power infrastructure in their application was painted this color, and it actually made it safe and easier for the maintenance staff and the operations staff to work with. So those kind of things should be on the table, at least as an option for these types of UPSs. NiCad batteries or lithium-ion batteries instead of traditional valve-regulated lead acid. Supercapacitors, otherwise known as ultracapacitors, for short backup time applications, either incorporated in the UPS or in a line and match cabinet. Metal-plated bus bars to avoid corrosion, external transformers or internal transformers, frequency converters. In other words, I have an application where I have 50 hertz utility input coming in, but the equipment I'm supporting needs to run at 60 hertz. So the UPS needs to take 50 hertz in and provides whatever voltage at 60 hertz out. Remember that these types of UPSs will not have the luxury of a bypass, since the frequency of the output is different than the input. But frequency converters are common for most UPS vendors that make industrial UPS. And then the necessary certificates for marine application that we saw in one of the previous slides. This shows a couple of shots at installation for a transformer-based industrial UPS where the transformers housed in the cabinet along with the UPS electronics, the way we used to do it back in the good old days. So let's talk a little bit about the evolution of mission-critical power. UPSs in general have been there to basically wait for the next power outage and bridge the gap while the generator starts up out in the backyard. Maybe in the meantime, they provide power conditioning, voltage regulation, frequency regulation, power factor correction, et cetera, in the form of power conditioning for the client. But in general, it's a pretty big investment, whether it's an industrial investment or an IT computer system backup investment in both power electronics and batteries. And traditionally, the UPS batteries had to be changed every 5 to 6 years if they're valve-regulated lead acid, which means I need to budget over the lifetime of a 15 to 20-year UPS. I need to budget full battery replacements in years 5, 10, and 15 maybe. That's pretty disruptive to the operations of my critical enterprise, and it's also very expensive to replace all those batteries. That's why we see the advent of lithium batteries with UPSs, because of their usually guaranteed 10-year service life and expected service life in UPS applications approaching 15 years. That depends on temperature and depends on the number of cycles, but primary reason we get longer longevity from lithium-ion batteries is their ability to withstand, in some cases, thousands of charge-discharge cycles, which is much more than I would find with a traditional UPS battery. So the advent of lithium batteries with UPSs opens the door to some new applications that we'll look at on the next couple of slides before we finish up here. We are finding, by the way, as are our competitors, that from a quotation, in some cases a shipment standpoint for larger UPSs, that almost 30% of them now are going out the door with some type of lithium-ion battery. Even though they're still a bit more expensive, they have much longer service life. So the question we're asking here is, rather than make this huge investment so the UPS can wait for the next power outage and be there to support you, a lot of the finance folks in these critical industries have said, gosh, that's a big investment. It takes up a lot of floor space. It costs a lot. I got to do maintenance contracts for the UPS, maintenance contracts for the batteries. I got to change those batteries every 5 years. The down the road total cost of ownership is significant as well. Is there a way to monetize this investment beyond just battery backup? So what we're talking about here is the ability to use a UPS and typically a lithium battery to reduce my operation expenses through cost avoidance. Do things like you can see on the left-hand side of this slide, do peak shaving at particular times a day. What we're talking about is slowly discharging the extra battery capacity that I might have in that UPS and utilizing the extra kilowatt capacity to basically reduce the demand that I draw from incoming utility power. Now, this does not mean that we would discharge the battery below what we need to support the critical load for X number of minutes. But it does mean I'm using the UPS's battery capacity and kilowatt capacity when available to help decrease the amount of power that I have to pay for from the utility company. And if I have time of use rates, for example, where at certain parts of the day during peak hours, the cost of incoming power to your enterprise can double and sometimes triple or worse. It'd be nice to be able to use some battery capacity there so that I don't set that peak, I don't draw that excessive current during the peak parts of the day. And when do I recharge that battery? Maybe from 1 to 3 a.m. when the cost of power is at its lowest, when the energy peaks are at their lowest. So that helps reduce operational expense. And through these types of programs, I can generate revenue with this UPS, or at least reduce my power bill through existing utility or grid operator programs. And these are programs that exist today, and we do have quite a few clients that are using their generators, for example, to provide some of this peak shaving, demand charge management or avoidance, et cetera. Now, demand response, different than demand charge management, you see on the right-hand side of the slide here. Look at it from the utility company's perspective. They need to balance their demand on the hottest days of the year or the coldest days of the winter. And if they have a large UPS or a large bank of generators or a campus environment like a hospital that has 15 or 20 large UPSs with large battery banks, it can be aggregated together to act like one big UPS and battery resource. That allows them to actually be able to do things like balance their loading without having to kick on the other big power station or power generating station down the road. This works, as you can imagine, on a fairly large scale, but the programs for paying the participants are already in existence, and the companies that handle the aggregation capabilities of multiple distributed energy resources, whether it's a big industrial UPS installation or a wind or solar installation down the road or on the other side of town or on the roof of the building, and have them all act together as what's known as a distributed energy resource. And the idea is to be able to, first of all, move towards more renewable sources of energy and energy storage, but also to be able to balance the demand and not have to kick on a big natural gas peaker plant or even build that particular plant that's being considered because I have enough distributed energy resources available to do that. Might even be able to use the UPS to help the utility company regulate their frequency. Under high load conditions, the utility frequency drops a little bit. It's not allowed to drop much or else they have to take expensive action. Or they can basically regulate frequency in the positive direction. If necessary, if frequency drifts too high, the UPS can charge batteries during that time and actually reduce that. So those capabilities use traditional UPSs, traditional features with a few extra controls, and typically a lithium-ion battery that can tolerate the more frequent charge-discharge cycles that are necessary there. So this expands the role of the UPS, at least potentially, and this is a brand new capability that we see showing up in the industry from a variety of UPS vendors, but it was done at the request of some of our larger users because they, again, want to monetize and get better usage of the UPS and battery systems that they've invested so heavily, and they know they require that capability to ride through power outages, but they want to be able to monetize that investment. Okay, so that brings me to the end of our session here, and we're a little over time, it appears, but if anyone is still hanging in and would like to ask some questions, or if there's questions in the chat that we can take a little time to help with, we'll be glad to do that.
Yeah, Ed, that was a great presentation. Thank you so much. And we do have a few questions already. And like you said, we are a little bit over, but if you still have a question, please feel free to submit it in the Q&A box because we can forward these along after the webinar to get the answers for you. So our first question is, why are bypass fuses necessary in large industrial UPSs?
That's a good question. Always like these. That's an excellent question. And in the older days, back in the days when I still had hair, we didn't put fuses in the bypass because we didn't want a device in there that could perhaps cause a failure of the critical load if the fuse were to fail unexpectedly or at a lower level than we would intend. However, UL and fire codes and electrical codes got involved quite a few decades ago and said you will have protection in the bypass line. So as a UPS purveyor, in general, we recognize that there'll be protection upstream of the bypass and probably protection in form of fusing or breakers between the UPS and the critical loads. So we try to size the bypass fuses and the speed with which they operate to accommodate to where they would be the least likely fuses in the series there to open up. We don't want something in our UPS equipment to disconnect and cause a failure of the critical load unless it's absolutely necessary because, let's say, of a bolted fault or an extended overload condition. So the bypass fuses, often by design, are the largest and slowest acting fuses, and we depend on upstream and downstream protection that's particularly downstream protection that's closer to where a fault or overload might occur that can be more discriminatory in protecting and isolating a short circuit or a fault.
Okay, thank you for that. On this next one, I know you sort of touched on this a little bit in highlighting that they are seismic rated, but could you discuss some of the special features available for seismic zone compliance?
There are several different ways of addressing these, and some requirements like the IBC Zone 4 requires that the UPS remain in place during a seismic event. It doesn't necessarily have to remain operational, whereas OSHPOD, which is originally a hospital-related seismic requirement, started in California and is becoming more and more widespread. It requires that the machine remain functional during and after a seismic event. So what we do in the design of the UPSs and the battery cabinets, which are really the heaviest piece in a UPS system, is that requires, at a minimum, some special bracketry and some definition of the kinds of bolts and hardware and cement that's placed in the floor of the UPS room that we can bolt that cabinet down to where it will not move under typical seismic conditions. More likely that you'll see extra cross bracing and specific mechanical structural design elements that get added into a UPS design when we go for seismic zone 4 or OSHPOD compliance. So at the very minimum, you'll see floor brackets that have been specially designed to handle the loads and with a proper hardware. I'm talking about bolting that bolt to the floor and with the proper capabilities of the cement that floor is made of, and keep a UPS system in place under those seismic conditions. But it's more likely, especially for battery cabinets, to see extra cross bracing and extra support inside the cabinets so that it can withstand and continue functioning even after a significant seismic event.
Now, say you have a UPS that's already installed in a harsh environment. Are there any solutions to protect the UPS internally against adverse conditions, or is everything kind of, done while it's assembled?
Most of it is done while it's assembled, but if I have a UPS that's already installed and I'm worried that the environment may be worsening or getting worse, I can deploy things like drip shields above the UPS air intake. Remember, I don't want to block that intake, so I want to be careful how that's positioned, but I want to make sure that I'm not subject to moisture or water or condensation dripping in the top of the UPS, for example. I can modify or change the air filters that are deployed with that UPS, and a lot of air enters a traditional UPS around the door seals. So if those door seals are disintegrated or no longer present or not sealing properly, I can make some minor changes that don't cost a lot and put good quality rubber seals on the door so that all the incoming air is forced through the filter. And of course, I want to set up a procedure for checking those filters very frequently, like every 30 days or less, especially if I know I'm in a high dust or a high corrosive environment. So those kind of things can be done even with an existing UPS that's already deployed.
Okay, and then one more for you here. What is meant by high capacity rectifier and inverter? And would the capacity be greater than the UPS rating?
Usually would not be greater than the UPS rating, but that's an excellent question. When we say high capacity for a rectifier, for example, a rectifier usually handles the job of charging the batteries. So the client says, I've got a very large battery and I need it to be recharged very quickly. So that may mean that that rectifier is designed to direct more energy to the battery recharge circuit while still supporting the inverter. And technically that means the rating of the whole box goes up. So that's usually the reason for a high capacity rectifier. High capacity inverter is for those environments where I have a lot of motor loads, a lot of pumps, a lot of compressors, things like that, like, well, medical imaging devices would fall under that as well. CAT scan, PET scans, MRI, mammography machines that draw a large initial current. So that UPS inverter needs to be rated to handle, at least for brief periods of time, those high inrushes. So that may result in a re-rating of the UPS, but depending on the length of time that we support high inrushes, it's possible to, in firmware or in hardware, make changes that allow for that capability to handle those high inrush heavy output loads without changing the rating of the UPS. So a high capacity inverter may or may not change the rating, but a high capacity rectifier typically will change the rating.
Okay, well, that's all the time we have for questions today. Please join me in thanking Ed Spears and Jay Queen for the presentation, as well as our sponsor, Eaton. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple minutes to complete our survey. We strongly welcome your detailed comments. Please visit www.missioncriticalmagazine.com/webinars for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.